A Ukrainian artillery crew receives a target. The soldiers cannot see it. The target sits beyond the horizon, concealed behind terrain and several kilometers of contested ground. No forward observer is standing nearby with binoculars. No reconnaissance aircraft is circling overhead. The information arrives through a digital command system. A commercial satellite captured an image of the area earlier that day. Analysts compared that image with previous passes and noticed a change near a tree line. A reconnaissance drone then flew closer. Its operator confirmed the presence of military vehicles and transmitted their coordinates through a satellite-connected network. The artillery crew enters those coordinates into its fire control system. The weapon's navigation equipment uses signals from orbit to determine its own location. Timing data synchronizes the network. A guided munition uses satellite navigation during flight. After impact, another drone transmits video so the crew can determine whether a second strike is required. The entire engagement may last only a few minutes. Yet nearly every stage depends on space. Remove the satellite image and the target becomes harder to find. Disrupt the communications link and the coordinates arrive too late. Jam the navigation signal and the firing unit becomes less precise. Corrupt the timing data and the network begins to lose coherence. Blind the reconnaissance architecture and the artillery piece may still fire, but it fires into uncertainty. That is the central fact of modern warfare. Space is no longer a distant support function reserved for strategic headquarters or nuclear command. It has become part of the firing chain. Modern armies still fight with rifles. Aircraft still require runways. Ships still move through water. Yet the systems that tell those forces where they are, where the enemy is, and when to act increasingly depend on machines orbiting hundreds or thousands of kilometers above Earth. The next major war will therefore unfold across two connected battlefields. One will be visible. Tanks will burn, aircraft will launch, ships will maneuver. The other battlefield will remain mostly unseen. Signals will be jammed, satellite terminals will be hunted, ground stations will face cyber intrusion, commercial operators will receive urgent calls from governments. Engineers far from the front will discover that a software patch can carry the operational weight of an airstrike. Space has become the nervous tissue of warfare. The weapons still possess the muscle. Orbit increasingly supplies the senses. To understand why space matters, begin with the firing chain. A firing chain is the sequence that turns information into physical effect. A military force must detect something, identify it, locate it, decide whether to engage it, assign a weapon, and assess the result. The weapon receives most of the public attention because the explosion is visible. The preceding chain matters more. A missile launched at stale coordinates is an expensive way to rearrange empty ground. For most of military history, the range of a weapon was constrained by the range of human perception. An archer could engage what he saw. Artillery expanded that distance, but required observers who could report corrections. Aircraft pushed reconnaissance farther outward, though their presence exposed pilots to enemy air defenses. Space altered that relationship. A satellite does not need to cross the border in the conventional sense. It passes overhead according to orbital mechanics. From that position, it can collect imagery or detect electromagnetic activity across a vast area. The satellite may belong to a government. It may also belong to a commercial firm whose customers include insurance companies, agricultural planners, news organizations, and defense ministries. The significance lies less in the ownership label than in the compression of time. Consider a mobile missile launcher. During the Cold War, finding such a launcher could require a large intelligence apparatus. An imagery satellite might pass over the region and collect a photograph. That film might need to be physically returned to Earth, processed, examined, and sent through layers of command. By the time the assessment reached a weapons unit, the launcher could be gone. Today, a commercial imaging satellite can collect digital data. Automated systems can flag changes. Analysts can transmit coordinates across secure networks. A strike platform may receive the resulting target package while the object remains in place. Orbit shortens the distance between seeing and shooting. This compression changes military behavior. A force that once survived by moving every few hours may now need to move within minutes. Camouflage must deceive optical sensors and thermal sensors. Radio discipline matters because a unit can be discovered through its emissions even when hidden beneath trees. The battlefield becomes less forgiving because observation is persistent enough to make mistakes expensive. Persistence does not mean that one satellite stares continuously at one position. Many imaging satellites pass over a target only during particular windows. Cloud cover can obstruct optical systems. A clever opponent can use decoys. Terrain still matters. The deeper change comes from combining many imperfect sensors. A satellite image may reveal that vehicles entered an area. Electronic intelligence may indicate that a radar began transmitting nearby. A drone may then inspect the location. Each sensor reduces uncertainty for the next. The result resembles a relay race in which the baton is a set of coordinates. Space often carries the first runner. The artillery crew at the opening of this episode illustrates the mechanism. The satellite did not destroy the target. It made destruction possible by narrowing the search area. This distinction matters because military discussions often treat space effects as abstract services. Terms such as intelligence, surveillance, reconnaissance, positioning, navigation, timing, and satellite communications can sound like procurement categories. On the battlefield, they become verbs. A satellite finds. A satellite connects. A satellite guides. A satellite warns. The labels become operational actions. Take positioning and navigation. A military unit must know its own location before it can accurately strike another location. This sounds obvious, though armies spent centuries struggling with precisely that problem. An artillery piece cannot calculate a firing solution from coordinates alone. It also needs an accurate estimate of its own position. A small error at the launch point can become a larger miss at the target. Satellite navigation allows a firing unit to establish that position quickly, then move before enemy counterfire arrives. Timing performs a quieter role. Digital networks depend on synchronized clocks. Sensors record when events occur. Communication systems must coordinate transmissions. Financial markets and electrical grids also rely on precise timing, which is why space systems sit beneath civilian life as well as military operations. On a battlefield, timing allows separate machines to act as one system. A radar detects a threat. A command network evaluates it. An interceptor receives a firing order. Each stage must agree about when the event occurred. A few seconds may separate interception from impact. Modern war, therefore, depends on space in a manner closer to dependence on electricity than dependence on a particular weapon. A commander may never issue an order directly to a satellite operator, just as he may never speak to the technician maintaining a power generator. The entire operation still assumes that the service will remain available. This assumption is now dangerous. For decades, the United States and its allies treated orbital support as a dependable advantage. Opponents had limited means to contest it. American forces grew accustomed to precise navigation and continuous communications. That success created a habit. The habit became doctrine. The doctrine produced forces whose speed depends on orbital access. A military designed around rapid information flow becomes stronger while the network works. It also becomes vulnerable when the network begins lying. A lost signal is obvious. A corrupted signal is more dangerous. Suppose an artillery crew loses satellite navigation entirely. The soldiers know there is a problem. They can switch to maps, inertial systems, or surveyed positions. Their operations slow, though discipline can compensate. Now suppose the system reports a plausible location that is wrong by several hundred meters. The crew may trust it. The firing solution appears valid. The weapon functions exactly as designed. The shell lands where the mathematics commanded. That is the cruel wit of electronic warfare. Sometimes the machine works perfectly on behalf of the deception. The contest for space support, therefore, concerns confidence as much as access. A commander must know whether orbital information can be trusted. Once that trust weakens, every decision requires another check. Tempo declines. Hesitation spreads through the force. The side that restores confidence first gains an advantage even before it restores full capability. Once an army depends on a service, the enemy gains an incentive to attack it. This does not mean that every space war begins with a missile striking a satellite. Physical destruction creates debris and may produce political consequences far beyond the immediate operation. A sophisticated opponent has quieter options. It can attack the signal. Satellite communications appear global from the user's perspective. A terminal points toward the sky and connects a unit to a wider network. Yet the path contains several vulnerable components. The terminal itself can be located. The radio frequency can be jammed. The software can be compromised. The ground infrastructure managing access can be attacked. The satellite may remain healthy while the service collapses. This is one of the most important lessons from the war in Ukraine. The opening phase showed that commercial space systems could carry direct military importance. It also showed that attackers would seek vulnerabilities throughout the architecture rather than treating the spacecraft as the sole target. A satellite network is better understood as a long chain than as a box in orbit. The chain begins with the spacecraft. It continues through radio links. It reaches gateways and network operation centers. It passes into terrestrial data systems. At the far end sits a user terminal, often operated by a tired soldier in mud or snow. An adversary needs to break only one part at the right moment. The terminal deserves special attention because it converts an orbital service into a battlefield effect. Without the terminal, the satellite is a lighthouse shining toward an empty coast. Terminals can emit detectable energy. Their transmissions may reveal a headquarters or firing position. Enemy forces can use direction-finding equipment to locate the source. A system intended to connect a unit may also advertise where that unit is hiding. This creates a tactical dilemma. The commander wants continuous connectivity because the network provides current intelligence and rapid orders. Continuous transmission may expose the command post. Remaining silent protects the position but weakens awareness. The answer is disciplined emissions control. Units transmit briefly. Antennas use narrower beams. Networks shift frequencies. Commanders distribute their headquarters so that the loss of one node does not silence the formation. These practices sound like technical housekeeping. Under fire, they become survival skills. Jamming presents a different problem. A jammer does not need to destroy the satellite. It floods the receiver with interference or overwhelms the desired signal. The effect can be localized. A country may disrupt navigation near the front while leaving the wider constellation untouched. That local character makes jamming attractive. It can be turned on and off. It may remain below the political threshold associated with kinetic attack. The attacker can deny responsibility or describe the disruption as defensive activity. For the soldier, the legal distinction offers little comfort. The map marker begins drifting either way. Navigation warfare has therefore become part of ordinary combat preparation. Forces need alternatives to satellite navigation. Inertial systems can estimate movement without external signals, though their errors accumulate over time. Terrain matching can compare observed features with stored maps. Celestial navigation has returned to military discussion, which is a fine reminder that warfare sometimes moves forward by rummaging through an old drawer. The answer is rarely to abandon space support. The military value remains too great. The answer is to design forces that can absorb intermittent loss. Resilience is often discussed through satellite numbers. A constellation containing hundreds of spacecraft is harder to disable than a system built around a few large satellites. If one vehicle fails, others may carry part of the workload. Yet orbital proliferation solves only part of the problem. 1,000 satellites do little for a battalion whose terminal has been compromised. A resilient constellation paired with a brittle ground network produces resilience in PowerPoint and fragility in combat. The architecture must survive from orbit to user. This requires forces to train under degraded conditions. A unit should experience navigation failure during exercises. Communications should disappear without warning. Commanders should discover which decisions they can make locally when higher headquarters becomes unreachable. Such training can feel artificial in peacetime because instructors know when the outage will end. Real combat offers no such courtesy. A commander may not know whether the disruption will last 30 seconds or 3 days. That uncertainty shapes behavior. A centralized force suffers more because subordinate units wait for instructions. A force with clear command intent can continue acting. Space resilience therefore becomes a question of command philosophy. The technology matters, so does the human arrangement beneath it. This is where military organizations often confuse redundancy with resilience. Redundancy means possessing another system. Resilience means continuing the mission while switching to it. A backup radio stored in a vehicle is redundant. A crew that has never configured it possesses a decorative brick. Space-dependent forces face the same problem at a larger scale. They may own alternative communications paths or navigation methods. If those alternatives require unfamiliar procedures, separate security credentials, or rare technical specialists, they may fail during the exact hour they are needed. The enemy counts on this friction. An attack on space support seeks more than technical denial. It seeks organizational delay. The attacker wants staffs to argue over whether the data is trustworthy. It wants operators calling help desks while targets move. It wants commanders to postpone action until the picture becomes clear. War rarely waits for clarity. It charges rent on every minute. Cyber operations deepen the problem because they can target the systems that manage satellites rather than the spacecraft themselves. Ground control networks issue commands, they schedule access, they process data, they distribute products to users. These functions depend on software and identity management. An attacker who gains access may steal information. A more dangerous intruder might manipulate it. The attack could alter tasking, so a sensor looks at the wrong region. It could corrupt metadata attached to an image. It could interfere with authentication and lock legitimate operators out. The visible satellite would continue passing overhead. The mission could still fail. This is why space cyber defense cannot be separated from terrestrial cybersecurity. The orbital platform may be exotic. The attack path may begin with an ordinary credential. A phishing message does not become majestic merely because the victim operates a satellite. The mismatch is almost comic. Billions of dollars in orbital hardware may depend on whether one employee recognizes a fraudulent login page. Strategic competition sometimes wears steel armor and leaves its shoelaces untied. The rise of commercial space has changed who can obtain orbital support. A state once needed a national space program to receive high-quality satellite imagery or dependable satellite communications. That requirement favored wealthy powers. Smaller countries relied on allies or accepted long delays. Commercial constellations have lowered the threshold. A government can purchase imagery as a service. It can lease communications capacity. It can gain access to data produced by companies operating fleets of satellites. This does not erase inequality. The strongest states still possess classified sensors and protected military networks. It does change the lower boundary of participation. A country without its own constellation can still fight with space-derived information. Ukraine demonstrated the military significance of this arrangement. Commercial imagery helped reveal activity across a vast front. Satellite communications supported connectivity when terrestrial networks were damaged or threatened. Private firms found themselves making decisions with strategic consequences. This created a new relationship between governments and companies. A traditional defense contractor builds a weapon under government direction. A commercial space company may operate a global service for many customers. When war begins, the government may depend on that existing network rather than a purpose-built military system. The company then becomes part of the operational architecture without becoming a conventional military command. Its executives may determine where service is available. Its engineers may respond to jamming. Its lawyers may interpret contract boundaries, while soldiers depend on the answer. This arrangement moves private decision-making closer to the battlefield. That creates leverage for both sides. The supported government can gain capability quickly because the commercial network already exists. The company can update software faster than a traditional acquisition program. A large constellation may replace damaged capacity without waiting years for a new satellite. The opposing state gains a target with global business interests. It can threaten regulation, market access, infrastructure, or personnel. Pressure may occur far from the combat zone. A commercial operator must therefore calculate risk across several jurisdictions, while a military commander thinks about the next operation. Their clocks run at different speeds. The commander asks whether service will remain available tonight. The company asks whether today's decision changes its legal status or exposes its employees. Both questions are legitimate. Neither can be postponed forever. Commercial participation also complicates the distinction between civilian and military infrastructure. A single constellation may serve households and hospitals while also carrying military traffic. An attack intended to disrupt battlefield communications may affect civilian users. A company may be civilian in ownership while its service performs a military function. This ambiguity can deter attack because the political consequences become harder to predict. It can also invite coercion because adversaries may believe that commercial systems are less protected than military ones. The strategic challenge lies in setting expectations before the crisis. Governments need contracts that describe wartime access. Operators need channels for threat information. Military planners need to understand what the commercial service can actually provide under interference. A peacetime service level agreement is a poor substitute for wartime command arrangements. Commercial systems also introduce enormous quantities of data. Access to imagery does not guarantee useful intelligence. Someone must decide what to collect. Analysts must interpret the result. Networks must deliver the product to the unit that can act. The bottleneck may shift from collection to processing. A force can drown in orbital visibility. Thousands of images arrive. Only one contains the missile launcher that matters. Artificial intelligence can assist with change detection and object recognition. It can scan broad areas faster than a human team, yet automated classification produces probabilities rather than divine verdicts. Camouflage and decoys can fool models. Training data may fail under unfamiliar conditions. Human judgment remains necessary because the cost of error is physical. A model may flag a vehicle. An analyst must ask whether the pattern fits the wider situation. The commander must decide whether the confidence level supports a strike. Space expands the volume of available evidence. It does not remove responsibility from the decision. This matters because modern militaries often pursue sensor-to-shooter speed as though speed were always desirable. A shorter firing chain helps engage mobile targets. Excessive compression can also leave too little time to question flawed data. The best system is not the one that fires fastest under every condition. It is the one that matches decision time to the uncertainty of the target. A clear, hostile missile launcher may justify rapid engagement. An ambiguous shape near civilian infrastructure requires a different rhythm. Space systems make both cases visible. Doctrine must preserve the distinction. The commercial layer also affects deterrence. A state considering an attack on a military satellite may face a relatively bounded decision. It knows who owns the spacecraft and what mission it performs. A distributed commercial architecture presents a murkier target. The service may move through many satellites and ground stations across Allied territory. Disabling it could require a broad campaign. That raises the cost of complete denial. Partial disruption remains possible. Jamming can affect a region. Cyber attacks can strike a network segment. Physical attacks can target gateways. The defender's task is to ensure that no single disruption breaks the firing chain. This is why modern space power increasingly depends on mixtures of government and commercial systems. Protected military satellites provide assured service for the most sensitive missions. Commercial constellations provide scale. Terrestrial networks offer another path when orbital links are contested. The architecture becomes harder to destroy because it refuses to present one neck. Yet mixed systems create command problems. A user may need different terminals. Security classifications may prevent data from moving across networks. Commercial products may use formats that military systems cannot ingest easily. The enemy does not need to defeat the whole architecture if bureaucracy has already separated its parts. Interoperability sounds dull until the shooting starts. Then, incompatible data formats become a form of self-jamming. The lesson is plain. Commercial space changes the economics of access. Military effectiveness still depends on preparation before conflict. For defense leaders, dependence on space changes the meaning of readiness. A unit can possess trained soldiers and functioning weapons, yet remain unready because its data chain is brittle. Commanders should therefore judge readiness by whether the force can fight through interruption. The practical test is simple. Remove the satellite service during an exercise and observe what happens. Does the unit recognize the disruption? Can it distinguish jamming from equipment failure? Does it possess an alternate method? Can subordinate commanders continue the mission? The answers will expose weaknesses that ordinary readiness reports miss. Defense organizations should also treat terminals and ground systems as part of the weapons architecture. Protection cannot stop at the satellite. Cyber teams need visibility into mission networks. Electromagnetic warfare specialists need authority to identify interference. Operators need procedures that connect technical warnings with tactical action. A satellite anomaly report that reaches the artillery battalion 6 hours later is an autopsy. For commercial space executives, wartime relevance brings opportunity and responsibility. Governments will purchase greater capacity. They will also demand stronger security and clearer assurances. A company that markets resilience must prove that its service can withstand attack across the full chain. That means protecting software and ground stations with the same seriousness applied to spacecraft. It means designing terminals that can shift among available networks. It means rehearsing incidents with government customers before a crisis. Companies should also define the limits of their wartime role in advance. Ambiguity may appear useful during peacetime negotiations. During combat, ambiguity becomes a decision delayed under pressure. An executive should never first discover the strategic meaning of a contract while a military operation is already underway. For policymakers, the central problem is that space support now crosses boundaries built for an older era. Commercial assets can perform military functions. Cyber attacks can create strategic effects without visible destruction. Local jamming can disrupt civilian infrastructure while remaining difficult to attribute. Policy must therefore address behavior and effect, rather than relying solely on ownership categories. Governments also need stronger arrangements with allies. No state should assume that every useful commercial constellation will be domestically owned. Access may depend on foreign regulators or ground stations abroad. Coalition warfare has always required political trust. Space adds technical dependence to that trust. A coalition member may provide imagery. Another may operate the communications gateway. The fighting force may use a terminal built elsewhere. The chain works only when permissions and security rules have been settled. This is the quiet architecture of alliance power. The public sees the launch. The warfighter depends on the agreement signed years earlier. The broad estimate is that militaries will become more dependent on space, even as they prepare to operate without it. That sounds contradictory. It is the natural result of military value. Space services provide too much advantage to abandon. They extend awareness, they increase precision, they connect forces across distance. Every serious military will seek more of them. At the same time, every serious adversary will attempt to disrupt them. The future force must therefore be deeply connected without becoming helpless when disconnected. That balance will separate mature space power from technological vanity. The next major conflict may begin with familiar images. Aircraft rising from runways, ships leaving port, armored formations moving toward a border. The decisive opening action may appear far less dramatic. A navigation signal begins to drift. A commercial satellite terminal loses access. An imagery pipeline delivers yesterday's picture instead of today's. A command network rejects valid credentials. No explosion announces the attack. The force simply becomes slower and less certain. That is what makes space conflict dangerous. Its effects can enter the battlefield disguised as confusion. A commander may believe the target moved. An operator may blame faulty equipment. The headquarters may assume the subordinate unit misunderstood the order. By the time the pattern becomes clear, the enemy has gained hours. Future wars will therefore reward forces that recognize orbital disruption as an operational condition rather than a technical inconvenience. Watch the exercises. See whether militaries genuinely train without satellite navigation or merely discuss it at conferences. Watch commercial contracts. The crucial clauses will concern priority during crisis and authority over service boundaries. Watch the ground segment. Countries will spend heavily on satellites, but the more revealing investments may appear in protected gateways and alternate command sites. Most of all, watch how militaries connect space operators with frontline commanders. The side that translates an orbital warning into immediate battlefield action will preserve tempo. The side that traps the warning inside technical channels will learn too late that information can be accurate and useless at the same time. Space does not replace land warfare. It changes the quality of every decision made within it. It does not replace naval power. It allows ships to operate across oceans while sharing a common picture. It does not replace air power. It helps aircraft navigate and receive targets beyond the pilot's view. Modern warfare still ends with physical control, physical destruction, or political surrender. Space shapes the path toward those outcomes by determining what each side can perceive. The artillery shell remains lethal. The orbital architecture tells it where the war is. And in the next conflict, the first force to lose sight of that architecture may still possess its weapons. It may simply discover that it no longer knows where to point them.